Hello, everyone. Welcome to today's developer coaching webinar. My name is Tara Van Cleve, and I'm part of the developer relations organization here at Oracle. Today, we're excited to dive into the core principles of context and memory engineering and to show you via live demos how they shape modern agent design. If you have any questions, we've enabled the Q&A section of the Zoom and we'll answer throughout the hour, as well as leave some time at the end for any remaining open questions. Today's webinar will be presented by Richmond Alake, Director of AI Developer Experience. So without further ado, Richmond, over to you to take it away.
Thanks a lot, Tara, and thanks a lot, guys, for joining us. We've got the hour, and we're going to be talking about some really cool topics. So, firstly, I always like to ask folks where you guys tuning in from. Use a Q&A button on this on Zoom, and you can just tell me where you're coming in from. I'm tuning in from UK, just on the outskirts of London. And we are going to have fun today. So let me start by actually sharing my screen. We're going to spend a bit of time going through some presentation just to set the context, and maybe we'll spend the rest of the 60 to 70% of the time going through some code. So we are going to be having a lot of information sharing today, all centered around memory engineering, agent memory, and context engineering, and how Oracle AI Database is the universal memory core for AI agents. And there's going to be a lot of keywords, but I am going to be explaining everything. So use the Q&A box to let us know where you're tuning in from. So what we're going to cover, we are going to be talking about the journey so far. The whole Gen AI space is exploded in a very short amount of time. So we're going to do a quick recap of where we came from, where we are, and where we're heading to. I'm not going to be doing any predictions. We're also going to understand a bit of context engineering and have an overview of context engineering. We'll talk about the context engineering flywheel. Then we're going to be talking about agent memory as well. What does that mean? How do we implement it? And then we'll be talking about memory engineering, augmented agents, and what does it mean to be the memory core for AI agents. And of course, there's going to be some code. We're going to be doing some demos, and you are all going to get a link to where the code for presented in this webinar is. So it's going to be on the Oracle AI Developer Hub GitHub repo, and you're going to get a link to that repo, and the code is going to be there within the next few hours. But the best part about this is, one, I get to talk to you folks, but the other best part about this is you guys get to ask me questions. Anything happening in the space right now, you guys can ask me questions as to what you're seeing. There's a lot going on. There's a lot of keywords in the space. Just this week, we're hearing a lot of people talk about agent loop, agent harness, where there's a lot of people talking about that there is Claude bot or Molbot and just a bunch of keywords. And my job is to provide some clarity into what we're seeing in the AI space today. So there's a lot of people tuning in from Las Vegas, Nashville, Manchester. That's good. A lot of people from Dallas, London, and that's good as well. So yeah, keep that coming in, guys. And obviously, if you have questions, don't be afraid to ask. There are no stupid questions. So the journey so far, let's start off there. So we have a bunch of checkpoints, and I'm just gonna talk about four main checkpoints that we've gone through. And when I say we, I mean us as an industry. So we've essentially started off with this LLM powered chatbots. With these are chatbots that have an embedded LLM behind them. And what we're able to do was give them a query or prompt, and then they gave us a response in natural language, which was great. But one thing we realized is we needed the response to be more personalized. And that took us in the world of RAG application, retrieval augmented generation. And I've got a bunch of charts here, a diagram here, but very quickly, I'm going to explain what RAG is. I'm not going to go too much into details. There's loads of videos that we've done on this channel on what RAG is and what agents are. So I'm just going to go over it quickly so we can get to where the meat of this webinar is. So RAG applications essentially means that with the whatever that we're providing to the LLM, what the user prompt that we're providing to the LLM is supplemented with a bunch of user domain or problem specific data. Now that data could come from the environment or data source or an API, and then we pass it into a data processing pipeline. We have our metadata and a bunch of chunks. We pass that through an embedding model, and then we're able to get a numerical representation of a data object. Now, that numerical representation of a data object is called an embedding. And what we can do with that is start to do things like semantic search, which is just a fancy way of saying we are searching by meaning. And Oracle AI Database allows you to actually do vector search using different distance functions. So again, we've spoken about that in previous video, just going over things a bit quickly. So people are still telling us where they're coming from. We see folks from Texas, Dallas joining us, which is great. And it's morning over there, I believe, or it's morning somewhere in the States. So thanks for joining us very early in the morning. So we can go into that's what vector search is, and whenever a user ask a prompt to a LLM application or a RAG application, they would get a response that is actually grounded in domain specific data and also using that natural language response you get from the LLM. So that's checkpoint two. Let's go over to checkpoint three. Now, checkpoint three and checkpoint four are happening simultaneously because a lot of times today we see that a lot of developers and a lot of enterprise organizations are implementing either automated workflows or autonomous agents. And there's a difference because autonomous agents have this, it's basically this intelligent entity that has access to different tools and they can perform actions based on the input. But with an LLM driven workflow, you have different steps that are outlined that can be taken, and you might have different routes, and in between these routes you might have a LLM that gets to decide where the route where the execution step goes, or you have LLMs within a process to help create natural language responses or conduct some different computation. But ideally there is no, or there isn't a massive level of autonomy in an LLM driven workflow. And you can see in this one we have on the screen, there's a certain path that leads to the LLM providing a response to the user, but there are certain path that actually leads to a human getting a human coming into the execution, the control flow, and actually taking over the execution. So this is the benefit of a LLM driven workflow. Next, we got into the next checkpoint is agentic application. So this is the sweet spot. This is where we want to go. We want to have AI agents that are able to act on our behalf. And the key components of an AI agent is essentially memory, action, perception, and reasoning. And the reasoning is enabled by the LLM. And then you have perception enabled by inputs we pass into the application. This can be audio, this can be text, this can be image and video. And then for actions, there are different ways an agent could take action. So you can take an action by using some of the system resources that exist within your infrastructure. This can be code, functions, and also you can have MCP. You can actually use some MCP servers and actually conduct actions through them, or just connect to the internet through some APIs like Tavily, XR, Firecrawl that just gives you access to the internet. And all of this are action based. Now, the best thing about an AI agent is they need to remember. And AI agents essentially are better than most of the stateless LLM chatbots that we see because the ones that are memory augmented have the ability to actually remember who you are and remember your preference and give you more personalization and a personalized response. And memory is one of the biggest buzzwords of 2026. We've seen OpenAI, we've seen Anthropic, we've seen a bunch of folks trying to solve memory and release memory as a feature within their commercial product. So today we're going to be looking at how we as AI developers can actually implement our own memory augmented agents. Okay, so but the key thing of what enables memory is the AI database, and that right here is the Oracle AI database. So we're going to be going through all of the keywords, all of the buzzwords. But if I say anything that you don't understand, or if you're curious, just use the Q&A feature just to ask me any questions, and I'll do my best to answer. So let's talk about the problem that we're actually solving. We have LLMs, and LLMs have a bunch of constraints. And one of them is instruction sensitivity. So in the early days, I think most of the reasoning models that we have today, such as GPT 5.2 or 5, and we have the Claude models as well, and most of even the open source one, they have really good reasoning capabilities that allow them to follow instructions more tightly than the predecessors. And what we're able to see, what we used to see back in the day, maybe a year or two ago, is whenever we provided instructions for LLMs to follow, sometimes they followed it, sometimes they didn't. And obviously, this is because LLMs are inherently probabilistic. So they're actually sampling for a bunch of tokens. They're actually sampling for a bunch of tokens to give you some prediction or next token prediction to answer that question. So we saw a lot of LLMs in the early days just steering away from the initial instruction, and this gave birth to this role description of prompt engineering because we started to use, I guess, some linguistic patterns to make sure that the output from the LLM is maintained in several terms and is as we expect. But this again, there was another constraint within LLM, which is the bounded context window. So LLM can today now they go over a million plus tokens, and this context window is the amount of information an LLM can take at a single inference step, and this is calculated by the number of tokens. So tokens are now in the 1 million, or typically GPT-4 probably has around 258, I think, or 128, one of those ones. But it doesn't matter if you're using a million token enabled LLM because there is another constraint of LLM is they have a form of positional bias, right? So some of you might have heard that the information in the LLM, if you were to put it at the start, it pays more attention to it, or maybe if you put an information at the end, it pays more attention to it. But we have information in the middle of the context window that seems to get lost. That's another constraint. And the biggest one that we have and we're going to be talking about today is LLMs are just stateless, right? They can't remember information that you provide to them in terms of the next turn that they're taking, unless you're saving conversations to an external store or to an external memory. But just out of the box, they are stateless. Now, there's a bunch of disciplines that have emerged from the space of agent engineering or AI engineering to solve some of these constraints. So, prompt engineering is a popular one, and now we're looking into the realm of we're going into the realm of context engineering that is used to solve the bounded context window and positional bias. So we have a bunch of techniques that are solving that. And for statelessness of LLMs, we have memory engineering as a discipline to solve that. So if you're an AI developer, you're building some AI applications, or you're building an agentic application, look into some of these disciplines, or you might find yourself using techniques from some of these disciplines, a lot that we're going to be going into today. So let's talk about um, context engineering. So with context engineering, we're going to define it in a second, but let's just look at what usually makes up the context window. The context window is made up of a bunch of information and they usually play a role. So we can start with the system instruction. This is usually some instructions that you will put as a developer to determine to let the LLM understand maybe its environment that it's operating within, how you want it to operate as well, and some of the maybe capabilities that it has as well. Then there are things that have emerged today, such as Skills MD or Agents MD, which are markdown files that actually describe to an LLM maybe some routines or ways of doing certain tasks that you've specified within the environment, within your operational environment. So Skills MD is one that the Claude models are can utilize, and every time you run a Claude model, they will usually look for a skills MD file to understand how you want them to execute a task if specified, along with other things such as code execution or MCP utilization as well. And the same thing for Agents MD. Agents MD is more generalized, and all the models, at least the GPTs and Claude, are aware of how to utilize an Agents MD. Then you have your own developer instruction that you can put in there. In the code, I'm going to show you some example of developer instructions that we can pass to a GPT model. Then, because some of the reasoning models we have today are able to use tools, they're able to do things we call function calling. We actually have to pass the tool schemas into the context window as well, just to give the LLM an awareness of the tool capabilities that it has. Then in the context window, you're obviously going to have some retrieved context. This is information about the problem domain or information about the user. It can be that is retrieved through RAG, or you could have it as memory as well. Then you have your conversation history. So past interaction that you've had can be passed into the context window, and then you have the current user message. Now, this is a rough example of what the context window composition is typically made of during an inference step. But one thing I wanted to mention here is how how easy it can be to actually go over the context window capacity. And context window capacity is how much token the LLM can actually take at a single inference step. So 128, I think, is the GPT-4 context window capacity. So imagine if you had all of this instruction and it took up 100,000 tokens, and you have to leave some tokens for the output. You have to actually leave some tokens for the output produced by the LLMs. In your next iteration, once you put the previous turn into the conversation history, you're going to run into a problem, which is you're going to exceed your context window capacity. So you're just going to get into a failure mode with your inference step. So you're going to go into problems that we as a field have started to define as context bloat, right? Stuffing your context with a lot of information leads you into context bloat, and you're going to start going down a path of having different failure modes. Another issue you can get with just stuffing a bunch of context is into your context window is context rot as well, which is even though the right information might be somewhere in the context window, it's actually not discoverable, or it's actually just lost in terms of with other contexts that are maybe even irrelevant to the current objective that is being executed or being addressed. And these are, I should have mentioned, but these are from OpenAI over here. OpenAI have shown the composition of how they see the context window within the agent loop. So I believe that this particular piece is called unrolling the codex agent loop. So you can go look into that. Very good piece. Anthropic did the same when they were also talking about prompt engineering versus context engineering. This piece is called effective context engineering, and they also give a lot of different principles and mental models to think about context engineering, which I'll be providing you today as well. As you can see, there are different ways we're composing the context window, but the key thing is we've moved away from just the world of prompt engineering where we have to put a bunch of information and tell the agent to tell the agent that your dog is dying or something, or else you won't be able to make sure it answers the question. We've moved away from that into thinking constructively as to the information that goes into our context window, because we have better reasoning model. They can reason better about the instructions we're giving them, allowing removing the ambiguity in the output that we used to see before with the earlier models. So we're in this world of context engineering where we are more concerned with making sure we have the optimal set of information in the context window as opposed to putting as much information into the context window. So that's what context engineering is a bunch of techniques that essentially ensure that you actually fill the context window with some high signal tokens to actually get better output. And the key thing about context engineering is you're always aware of the budget of the context window capacity. And I'm just going to be looking at time because I do want to get to the code and show you guys some of the good stuff the team have prepared for you. So with context engineering, there are a bunch of techniques. And some of these are not going to be alien to you. Some of them might be very familiar, in fact. So we're going to start with context reduction. This is just simply reducing the context window, reducing the information in the context window. Then there is context retrieval, which you can guess is just retrieving context. How do we retrieve context? There are context engineering techniques that are actually designed to help solve context retrieval. But to be honest, in my opinion, we're going into the realm of memory engineering once we start to talk about retrieval, especially when you're doing it from an Oracle database. So next one we have here is context organization. Organizing your context is very important. That how you structure information is very important for a different reason. One, to prevent lost in the middle problem that we have by context stuffing. But two, some of the LLMs that we utilize have a caching mechanism at the model provider operation. So when you actually send when you actually send information in a context window, OpenAI or other model providers might be caching the information because calculating the attention of each token is actually computationally expensive. And if you're continually providing the same information, your model providers might be actually just caching all of the calculation is done previously. And this can save on latency and operational costs for both yourself and the model provider. So context organization is very important. And I've already mentioned context window monitoring and context offloading. We're going to see all of this in action, actually. So context engineering, I really want to talk about context reduction because I think it's the easiest one to implement for most developers. And the two, and developers tend to conflate this. There's a difference between context summarization and context compaction. Summarization is typically done in essence with an LLM or with a language model. And what you would do is pass in the uncompressed context into an LLM, give it some instruction on how you want it to compress the information, and it would give you a compressed version. You typically want to use maybe a small language model for this just to reduce the latency, and as opposed to you using a more powerful model like a GPT 5.2. Then context compaction is a context reduction technique, which essentially you're just removing information from the context window. You're not taking it through any process. You're just removing a chunk of information. I've put some summary, some description there as to the two techniques and how they differentiate. But one thing is you guys are going to get the slides to this. You're going to get this presentation. You're going to get links to the code as well that we're going to be presenting later. But here we can see we have the full set of the content that goes within a context window. And imagine this is 120 tokens. Then using different techniques that we've spoken about, what you can do is actually start to remove information from the context window. So with context offloading, for example, you can take the tool outputs from the context window that has been done in previous step and just offload it to your database because it's always good to store in case you're working in some industries like finance industries where you're audited. You always want to store the tool outputs or maybe even for observability after a certain agentic run. But you want to offload, you want to remove some of the tool outputs and into an external memory store. Then another thing you might want to do is summarization, like I described. Now you look at the previous conversation history and you can summarize it and then insert the summarized conversation into the next iteration of a clean context window. Then you have context retrieval, which is another context engineering technique where you're retrieving only the actual information you need as opposed to stuffing all information you have. So for tools, you can actually dynamically retrieve tools, especially if you're saving the JSON schema in your database and you're using your database as a toolbox. So the way this would work is you would have the description and name of the tool, and you actually pass that through an embedded model, store the embedding in your database, and then just before inference, or when conducting inference, you actually get the user's query and you do a vector search operation on the tool vectors just to get the right tools for that certain objective. So that's how you can start to reduce a bunch of tools in your context window or a bunch of JSON schemas of tools that you have. And there are some downsides to this. For example, an obvious one is you're going to be breaking the organization of your context window at each turn if you're dynamically retrieving tools. And that means you're breaking the prompt cache. You're breaking the cache at the inference provider point as well. So we have a bunch of techniques that we're using to offload and remove context. And what that leads is a more compressed context window, right? You have more information that's compressed over your context window. And rather than you having 120 tokens, you have 50,000 tokens. A good piece that came out from folks at LangChain, a good piece came out from folks from LangChain just recently, and it talks about how they implement and actually trigger the summarization technique and the tool eviction technique as well. So this here will be the context summarization, and this here will be context compaction because you're just removing all of the tool outputs. So the piece is actually very good. It goes into a lot of details. That's some of the stuff we're going to be talking about today. I'll provide links to this in the email we'll be sending off as well, all of the pieces I've mentioned. So these are the key takeaways these are the key things I want you to take away. Prompt engineering is maximization, where we used to stuff a lot of information into the context window just so we can get the right output. But the reasoning capabilities of these models increased. And what we actually have is context engineering as optimization, which means we can take our time to actually select the right context to pass into the context window because these models can follow instructions better. Then memory engineering, which is my favorite discipline, is all about continuation, right? It's not just optimizing for the moment, it's making sure that the entirety of the context window, what comes out of it, what goes into it, and the environment around your agent loop is optimized for ensuring the agent can adapt to new information, can store new information, can also augment information to improve the recallability of an existing information. So this takes us to that realm of agents that are personalized, if that feel like you can actually trust and depend on them because they're reliable, believable, and capable. And this takes us into agent memory and memory engineering. Okay, so I'm going to take a step back here and we're going to talk about how humans memory work very briefly. I'm not a neuroscientist, but um, I've read a bit so we can understand how the human brain works. And you can just search how the human brain works and you'll be able to verify the things I'm sharing with you today. Human memory is not just one thing. Human memory is actually a bunch of different parts of your brain working together to give you the ability to remember and recall information. For example, we have long-term memory, which can store things like episodic memory. It could be for example, maybe a favorite birthday memory. And we have short-term memory, which can be information you're holding in the short term. I could tell you my phone number right now, and that will go into your short-term memory. But at the end of this webinar, you most likely will forget my phone number, hopefully. But there's sensory memory, there's working memory, there is semantic memory as well, there's associative memory. But the human memory is actually very complex. And one thing we can do as AI developers or just people operating in the technology space is to look at how nature has actually implemented some of the mechanism we actually look to replicate. And in technology, we've done this for years. So if you imagine planes, right? In the early decades of people trying to figure out how to create vehicles of flight, we looked to birds and the initial vehicles had wings that were flapping. But you look at the sky today, planes are not flapping their wings. What we have today instead are engineered planes. I don't know how planes work, or jet engine work, in fact. But you have planes that are engineered and they move much quicker than birds or any animals or flights we have today. So, taking that mental model, that paradigm, we can apply that to agent memory. How does human memory work? It's still an active area of research, but a little we know can go a long way when we look into computational intelligent entities, which means we can start to understand how human memory in in our implementation. And even in the realm of AI, we've always done this. We've always looked to neuroscience and the brain to inspire some of the neural networks that we use today in language models. So let's describe what agent memory is. And very quickly, it's a set of systems and techniques that essentially allow the agent to remember, and adapt, and actually approach the realm of continuous learning. And memory engineering is the discipline that is concerned with making sure those techniques are working and implementing those techniques as well. And when you get the slides, you can read a proper definition for it as well. So there are different types of memory that we can implement in agents today, and we're going to see some of them in a few minutes. You could take some time to look at the slides, but very quickly, we have short-term memory, long-term memory, and you can think of short-term memory as just an interim for information to be kept. So the context window is a form of short-term memory. So the LLM context window doesn't store state. If you actually in the next execution of your agent loop, in the next iteration of your agent loop, it will lose any prior information if you don't actually systematically store those information and retrieve it in the next execution or iteration. So that's a form of short-term memory. But long-term memory, you can have semantic memory, for example, where you have an existing knowledge base, an existing knowledge store, and you can have that connected to your agent via RAG or any other retrieval method that you have. And you can actually start to use that as a form of long-term memory that the agent within the agent loop can actually retrieve information from and use to answer a certain question or complete an objective. There are different type of long-term memory and different types of short-term memory. The key thing is I want you guys to understand the part of your system that is most concerned with memory. So remember this diagram we had at the beginning. Whenever I'm talking to AI developers, the part that you probably want to be concentrating on when it comes to memory is your embedding model, your database, and your LLM as well. And the reason why that is because that's the key part where information is held and information is retrieved from. But in the embedding model, you pass in information into the embedding model and you get a numerical representation from the embedding model. In an LLM, you pass in some prompts and what you get out is next token prediction, and you can actually get the output from that from the next token prediction. So, but in your database, you use that to store and retrieve information because the memory or the information within your neural networks, within this neural networks, are actually static, right? They're not changing with each iteration, but the information within your database changes with each iteration. And that's why whenever I talk to developers, I let them understand that the database is the memory core for your actual agentic application or infrastructure. There are other parts that are concerned with agent memory, but your database is where you want to put in most of your attention into, making sure that operation is optimized, the latency is low, the retrievals are optimized to retrieving the right information and tuning, which takes us into the realm of memory engineering. But very quickly, this is going to be the last slide I'm going to show before we get into the code. So understanding that there is in your agentic infrastructure, there is a memory core, and understanding how Oracle AI database can be that universal memory core is very important for when you're thinking about your architecture for your next project. So the nature of data in the whole technology space is heterogeneous, which means data comes in different shapes and form. You have JSON data, relational data, flat vectors as well, but you need a bunch of storage capabilities or storage providers to hold this data. One anti-pattern that I've seen, and it's reducing, but an anti-pattern that is very common is to have separate databases that handle different type of data you encounter. Now you can quickly see how that is not scalable, can get very expensive, and you might have to hire more developers just to handle a new database or an existing database. But what we are doing here in Oracle AI Database in Oracle is just focusing on a universal memory core that allows you to actually store any data within the Oracle AI database and give you all of the techniques and features you need to retrieve that data efficiently and with security. So this diagram, there's a lot going on in this diagram, but I try to use this diagram to show where prompt engineering, context engineering, and memory engineering meet in terms of the work we're doing. So over here in the memory core, you can see all of the concerns we have with memory engineering, such as memory retrieval, indexing, storage, decay and forgetting, retrieval optimization. These are all memory engineering techniques. Then once you start to operate within the context window, you get into context engineering techniques such as token budgeting, just-in-time retrieval, context organization and composition, context offloading, all the stuff we've talked spoken about. But also you go into the realm of prompt engineering once you're around the context window. So you're doing things like chain of thoughts or behavioral conditioning or few shot examples. So this diagram helps developers understand where does memory engineering sit, where does context engineering sit, where does prompt engineering sit. And I'm gonna see a bunch of questions and see which ones I can answer right now. So one question is, I know you're leading up to it, but can you explain the functionality difference in context eviction, skills, tools between database and files? Yes, I am leading up to it. So we're going to see that in a second. And let me look at the time. We've got 20 minutes, so it's right about a good time to go into some code. Take another question. Is there some tech stack for context engineering, or we do it by regulating off the order of connecting the system? So there isn't a tech stack for context engineering, and context engineering ideally is a bunch of techniques, and there isn't a specific infrastructure component you have to go and get. It's just a bunch of software engineering techniques. What you can do is look at some of the pieces coming out from folks like firstly Oracle, then folks like LangChain, Anthropic, OpenAI. Look at the applied AI team, look at what they're talking about, how they're managing context and optimizing their models, and that will give you an idea of how to implement your own context engineering techniques as well. So how can we refresh context window? Very simple. Firstly, the context window refreshes itself at every inference step if you don't actually pull in information from the previous iteration. And yeah, that was an easy question. Yeah, that's how you refresh the context window. So let's go into the code. All right. So this notebook does two things. One, it shows you how to implement agents that either uses a file system as memory or a database as memory. So, but the key thing I want to show you here is how you can think about agent memory and implement agent memory as well. I've already run this. I ran this just before we started this, just in case we have any hiccups, because live coding is usually live demos don't usually go the way you expect it. But very quickly, I'm just going to show you a bunch of information that I think is useful just in case we don't get to where we want to get to. So in terms of using files as memory for your agents and databases memory for your agents, the best way to actually decide is to implement it yourself and run some benchmarks on your specific workload pattern. And that's what I do here. I give you the actual code to enable this, and you're going to get the GitHub link to this particular notebook so you can run things yourself and see how we're implementing some of this context engineering and memory engineering techniques we're talking about. But I just put this quick notebook together where we have a file system, an agent that is backed by a file system, and an agent that is backed by a database. So the file system agent is called FS agent, and the other one, the database agent, is called mem agent. And I was just benchmarking the latency by how they can actually answer a question by retrieving information already in the store, then using an LLM as a judge to basically give me a good understanding of which one answered the best, then also looking at latency per query. But just from this test that I just did, which you can run yourself, you can just see very quickly the database has a lower latency, right? It has a lower latency in terms of retrieving information. And we also, the LLM as a judge says the database query are preferred. But the reason why the database has a lower latency can be quite obvious because file systems can be useful when you're working with maybe information that don't have as much content within them. So this is just text because when you actually start to use file systems for multimodal data, you start to run into a lot of problems. But I'm just gonna this is just for text basis. So for text, essentially what you're going to be looking at is short information. You can use a file system as memory, right? But when you start to go into several tokens long content, you actually have to have efficient method of retrieval, and we're going to be seeing that in action. And this is why the latency is lower with the database, because the database is actually optimized for production use cases where you're going to be working with millions of vectors and loads of information. And the database as a technology exists for a reason, which is to enable efficient storage and an efficient retrieval of information. So I was obviously I wasn't born in the 60s and 70s, but I'm aware that there was a principle or mental model of thinking of information within an operating system, which is the Unix philosophy of everything is a file or everything is a file descriptor. But I think we've come a long way from the 60s and 70s, and we have database technology. And for production use cases, you probably want to be using a database and not a file system for your memory. And this notebook goes into that, into more details, because we show ACID transactions, which basically means you don't want different agents conflicting in terms of when they're trying to commit some information into your database. So I show that in this notebook. But what I'm going to do right now, since we've gone through the results of this, I'm going to clear the outputs and we're going to run this live. And I'm going to go through some of the steps and point out the context engineering techniques, the agent loop, and also the memory engineering techniques that we have here. And we can start to run this cell by cell. And I'm going to increase the screen right here until it gets slightly uncomfortable and we can go. So the notebook has a bunch of narrative within it, and you're gonna need an OpenAI key. I'm also using Langsmith here for monitoring and observability because the outputs on the console on the editor is actually an ISO, and you can use a tool like Langsmith to actually just see the right things. So I'm going to run the cell right over here, and I'm also going to, apologies for the scrolling. We're going to be using the LangChain Oracle DB integration, which has all the search we're going to need. We're going to be passing in our environment keys. So bear with me a second while I get my environment keys here. And I'm sharing this with you because right after this webinar, you're going to get access to this notebook where you're going to actually be able to run most of this yourself and just passing in all the API keys I need. And okay, so for the file system agent, I'm just going to quickly mention what sort of functionality we're giving a file system agent. We're going to use LangChain to build an agent that has access to do some of operations that we are familiar with, which is to grep through a bunch of directories, actually read file, tell file, read a file range, and list some of the papers in our directory. So basically, all of the every functionality you need for a file apart from creating files, actually. So you have the ability to list, read, and also updating files. You also have the ability to list, read, and actually go into a file and look at certain segments using just some computational commands of your operating system. And this is what you have within your file system. And it uses this to store information into the actual file system as well. So you can see we have this episodic and semantic memory, which I explained what they were, but I'm going to delete them because we're running this from scratch. So when you actually use this notebook, you're actually going to have just the notebook and you can just run this and see how it executes. We're going to be seeing a bunch of techniques here, such as just-in-time retrieval, which is whenever you do context offloading or summarization, you probably want to put a placeholder of the location of the summarized context within the actual context window, especially for tool outputs. If you just want the agent to be able to just retrieve certain unsummarized context, think of it as a double click within the execution of the agent into some information. And you're going to see that in action as well. Then we have progressive disclosure, which is rather than passing all the file into the agent, we're actually just going to let the agent read the file by certain range when it needs to. Then when it gets the information it needs, it doesn't have to keep traversing through the file. And we've listed all the function we're providing the file system. And again, context engineering technique is to monitor your context window. So we're always going to be monitoring our context window. Then if it actually exceeds a certain defined token capacity, we're going to summarize the conversation, then create a new context window and pass in the summarized context. I'm going to be using LangChain basically for a bunch of abstractions, such as retrieving papers from archive. So for this particular use case, we're building a research assistant that we can ask different questions. And I'm gonna do something here. It's gonna be a bit of cheating. I'm just gonna run through all of the cell blocks and actually we can skip this or we could just re-enter this. I'm gonna run through some of the cell blocks so we can just see the agent in action. Then I'll just go through the key parts of the particular agent as well. Just have to enter all of this again. And while I'm at it, I might take some questions. Okay, so we're just going to run through some of the cell block and a dialog box is going to open for us to start conversing with the agent. And just going to quickly scroll down to where we're running the agent in part one, which is just essentially the file backed agent. And you can see the output here, and we can see that we're in the agent loop right now. So hi there, and hopefully no crashes. Okay, hello, how can you assist? How can I assist you today? And you can see it currently has episodic memory right here, and it has the conversation. We're going to look at that conversation in a second. And how can we, let's say, get me the mem GPT paper. So it's an archive agent that can search the internet, and what it's going to do is going to go into the internet and get the paper and actually store that in its memory. And that's what we can see here. It's told us I've successfully retrieved the paper titled memGPT, and it gives us more information about the paper. But the cool thing about this is we can see what the agent has done with the tools we've given it. So the first thing it did is it looked into archive and looked for candidates of the keyword, probably memGPT. And we can see that right here. We've given the agent tools, and it's using that tool, the archive search candidate that is defined in the notebook, using the keyword memGPT, and it's provided us with a bunch of candidates. Then it's used the fetch and save. When it got the right paper, it fetches the right paper, then it actually then it saves the paper. And someone is asking, can can I briefly describe the GUI tool we're using to display? Well, it's VS Code. Yeah, it looks like Jupyter Notebook. It is a Jupyter Notebook, but it's just Visual Studio Code and just running the notebook in Visual Studio Code. So excellent. So we can see the two outputs here, and this is context offloading, because what I'm doing is I'm actually removing this from the context window. I am putting it out into a file as opposed for it staying in the context window. So the code does this as well. And I'm going to ask it to get me the conclusion of the mem GPT. I'm just going to say paper of the paper. And just to show that it has memory, is going to remember what paper we're talking about. And we can verify that because what we can see is the tools it's using. So it's using the grep tool, and it's going into its semantic knowledge, and is actually going to look for, so it's looking for conclusion, and it's using the memGPT paper, which is the only paper it has, and it has this conclusion from the paper here, we introduced memGPT. So you can see it's actually not going to the internet to search for the paper because it knows it has the paper already because it's seen the conversational history in the context window. So it doesn't ask what paper, right? It doesn't ask what paper because it remembers we provided it with a paper. It remembers that it has semantic memory because we specified that in the system prompt. So I'm just going to exit here. And what you're going to see is the execution go into the database agent as well. So right here, you can see the output that we have. And Now we're going to go into the database agent and see the exact same thing, and then we could compare them as well. It decides not to go to the internet because it has conversational memory, which means that it knew that we already retrieved the paper in its memory, so it doesn't need to go to the internet again. It has the paper, it's just going to use what it has in its knowledge base. So this is a new agent. Just gonna go hi there, and I'm gonna scroll down so we can see the database backed agent. Okay, hello there. How can I assist you today? So this is a chat mem agent. We're chatting with the mem agent, and we just said hi there. Can you get me the mem GPT paper? And this is gonna do the same step. It has similar tools to get the mem GPT paper, but not only is it gonna get it, it's also gonna save it as well. So I found the paper you're looking for. It gave us the detail. If you like to access the paper, let me know. We can ask it, get me the conclusion of the paper, the concussion of the paper. Clearly, I can't spell. But here we're going to see it go through some of the same steps to get the conclusion of the paper and then output that to us. So we can see it's able to get us the conclusion from the paper. In this paper, we introduced MemGPT. So both of this memory backed system actually work, both file system and actually both file system and database. And I'm just going to interrupt the execution because now it's just going to go into it's going to go into the benchmark. So we can see we would go into our database using the SQL developer extension. We can actually start to see the content of our database. So we can go into tables and we can look at tool logs. And let's see, do we have some tool logs? Yes, we do. So the first thing we did was we search for archive papers, right? Because we asked it for MemGPT. Then it saved the paper. I've told it every time it searches, it saves the paper. Then it uses a third tool when we ask it to get the conclusion. It doesn't go to the internet again because it has conversational memory. It just uses the tool MemGPT conclusion because it knows we've been talking about MemGPT. If it didn't, you would have seen it go search on the internet for the same paper. But the key thing here is this. In both systems, we're able to log information. Agent memory is very important because you can start to log information and you can reuse information in more creative ways. So there are different types of memory, workflow, which is a type of procedural memory where you can pass failed or successful workflows into the AI agent at each step to help actually improve its success rate. So in terms of the memory that we have, what we're using for long-term memory here, just to show that we have a bunch of data and how data is stored in Oracle, we can see that we have this table that is essentially our semantic memory, and we've got each chunk of the paper. We went through the paper, we chunked bits of the paper and generated an embedding. So in one database, you have the chunks of the metadata of the paper, but you also have the vector embedding of the paper as well. So you can do things like semantic search. So this is the best bit. We're not using multiple databases to make this system work. And you guys are going to get the code and you can try it out. And that's it. That's the key thing. File system versus database. You probably, if you're doing a POC and you want to move quickly, you can use a file system. But as soon as you start to take your applications seriously and you want to go into MVP or actually want some customer to use this, you actually have to start thinking of using an Oracle database to actually allow you to store and retrieve different forms of data. Where can you get this code? This code is going to come through in an email to you guys that have attended and registered for this webinar. And you can go to Oracle AI Developer Hub and you can see examples of code like this. And that link will be provided as well. Or you could just type in Oracle AI Developer Hub. But you're going to get this code. In this code, I show you the benefit of ACID transaction guarantees that you get from an Oracle AI database and how important that is, especially when you get to production. And you could run that and let me know what you think. I'm just going to start sharing my screen again, and here we can see that the key takeaway is Oracle is the universal memory core for AI agents, and there's going to be a bunch of databases where you can actually use to store information. But the key thing is for AI developers to reduce the headache of infrastructure maintenance, use one database, use one memory core. It will help your AI agents and it will help you as an AI developer. And to end, we have the Oracle AI Developer Hub where the team uploads content every single week. So you can go to this Oracle AI Developer Hub, star fork, and watch the repo because this code is going to be uploaded right there in a few hours. And thank you guys. Over to you, Tara.
Thank you. All right. So this is a series, and Richmond will be presenting the last Thursday of every month. So definitely check back at oracle.com/developer/events. That is also where we're going to link the playlist with all of our replays as well. So the new one will be coming to you via email, but if you want to check out any of our previous events, please go and check that out at that website. And we'd also love to hear any feedback you have for us on today's session and on what you'd like to hear from us going forward, any upcoming topics. So as you exit the Zoom, there will be a quick survey that pops up. So please do share your feedback with us. And with that, I'd like to say thank you so much for tuning in and spending the time with us today. And we hope to see you at the next one. Thanks, everybody.